Talk about the tangents and normal. Like I said, you can't really use the word normal. You can see the way I describe it in the homework, like it's the perpendicular line to the tangent and pass through the same contact point as the tangent and the graph. So that's what we learned, and I said that's the focus for the sec as well. What we need to think about is what's the contact point, and do you know the gradient at that point? So it's A, FA, and F dash A. So do you know those two pieces of information? Okay, so after that, what we'll talk about is the rate of change. I think we talked about rate of change already in chapter 9, but we just mentioned again here. So there are two types of rate of change. The first type is called the average rate of change. Okay, the average rate of change. I don't really care about how the graph change in between 2 points. Okay, all I want to know is the difference in y values over the difference in x values. So basically you want to see from this point to this point, I don't care what happens in between. I just want to know how much it get increased or decreased in y value for how long of the x. Okay, so it's for per unit of x change, how much y get changed. So that's the average rate of change. Average rate of change, or for example, I have a diagram like this. Okay, it's a really messy diagram, but I have point A, FA here, and B, FB here. Okay, and I want to know the rate of change. Basically, I'm trying to find the gradient of that line. Okay, I'm trying to find the gradient of that line. So you connect them and find the gradient of that. And the second type is the instantaneous rate of change, which is F dash A. So at that moment, what's the direction? Well, the tangent can give you the direction of the movement of the particle. So what's the direction of movement? Like how steep like this tangent is. So it's the F dash A, it's the gradient of the tangent. Okay, remember F dash A is also means the gradient of the tangent. And tangent is also the direction of motion. Okay, we have mentioned that in chapter 9. So it's the direction of motion. Say if they give you a path, for example, the diagram I sketched above is the path for a particle. Okay, so that's how a particle moves. And then the tangent at each individual points indicate that at that moment, the particle tends to move in which direction. Okay, so if we sketch a tangent here, okay, like the particle at that moment trying to go that way, okay, along the tangent, but it's only for an instant, and for the next instant will change another direction. So that's a tangent also give you the direction of motion in application questions. Okay, so what's the positive and negative derivative means? So the positive derivative means is an increasing function. Okay, it's an increasing function. I haven't included the equals to 0 case. Okay, equals to 0, you need to see on the diagram whether it's increasing or decreasing part. But if you get dy dx greater than 0, that means there is an increase in y values corresponding to an increase in x. So your x change, your y definitely change. So for the derivative less than 0, there's a decrease in the y values when there's an increase in x. So when your x moves to the right, the y is actually the particle moving down. So after that, we have example 1 here. Okay, for the function with rule fx equals to x squared plus 2x, find the average rate of change in between 2 and 3. So what I will find is f2. Okay, I asked you to try this already yesterday. So f2 is 4 plus 4. That gives me 8. And f3 equals to 9 plus 6. That gives me 15. 4 plus 4, 8, 9 plus 6, 15. And then I will use the average rate of change equals to, we subtract the y value and subtract the x value. Okay, the value in the front must be a pair of coordinates, and this must be a pair of coordinates. You can't go 15 minus 8 and then divide by 2 minus 3. That's wrong. Okay, the vertically in the front must be 1 coordinate, and at the back must be 1 coordinate. So we have 7. Okay, we have 7. So for each unit of x increase, your y value increased by 7 units. And the next one is find the average rate of change for the interval 2 plus 2h. So we know what's f2, but what's f2 plus h? Okay, we replace x by 2 plus h. So what we have is 4 plus 4h plus h squared plus 4 plus 2h. And that is 8 plus 6h plus h squared. So the average rate of change in between those 2 points is 8 plus 6h plus h squared minus f2. Okay, that's f2 plus h minus f2, that's the 8 over 2 plus h minus 2. So you can see the bottom left with the h. Okay, that's h. And the 8 and 8 get cancelled on the top. We have 6 plus h. Okay, we have 6 plus h. So that's the average rate of change in between 2 and 2 plus h. We can check our value. How we can check it? So compare C2 and 3 and 2 plus h. So if h equals to 1, that will give you part A, right? If h equals 1, that will give you part A. So the average rate of change in part A is a 7. So we sub h equals to 1 here, we get a 7 as well, which means we get a right, well, 90% we get a right answer. Okay, so how I can make that it become a 3? So h equals to 1. So I increase 1 unit. So now the rate of change will become 7. It's the same as the previous answer. So that means we get a right answer here. And if I want to find the instantaneous rate of change at x equals to 2, okay, at x equals to 2. So what I'm trying to find is f dash 2. When you see the word instantaneous, you're trying to find the derivative at a point. So we're trying to find f dash 2. Okay, what we can do is we can derive fx and then sub 2 in. But there's an easier way in this question. Because I already find the previous line is 2 and 2 plus h. This is a very key feature, the 2 and 2 plus h. So if I can make lim h approaching to 0, revise on first principle, okay, that will give me the derivative at x equals to 2. Well, if there's a hence, okay, if there's a hence, you must use this method. Okay, if there's a hence, you must use this method because you must use something from the previous pass. But like if just say no hence, just say find the instantaneous rate of change at x equals to 2. What you can do is just find the derivative and sub x equals to 2. Okay, so you can do both ways in this question. But if I add the word hence, you must use my method now. So why I use this way? Because it's easier. I just get this from the previous line. That's just a 6 plus h. And that's just equals to 6. So f dash 2 is actually 6. We can double check it. So f dash x is 2x plus 2. And f dash 2 is 4 plus 2. And that equals to 6. So no problem with that. I can use both methods. This is a hence question. Okay, if it's a hence question, I will use the top line. If it's just say like this, I can use either of this method. Okay, for example 2. Example 2 says a balloon develops a microscopic leak and gradually decreasing in volume. Okay, so be careful with the word decreasing in volume. Okay, decreasing in volume means the rate of change is decreasing. Okay, when time increase, your volume is actually decreased. Your derivative should be a negative value. Okay, your derivative should be a negative value. What is the average rate of change for the first 10 seconds? Okay, you can see what, like, for the example 1, it tells you very directly, like, average rate of change or instantaneous rate of change. But in the application question, no one really make it that obvious. Like, they will say, find the instantaneous rate of change of V and T. They won't say in that way. What they will give you is in the context. But read the first sentence. What is the average rate of change? For the first 10 seconds, okay, from 0 to 10, you have an interval. Okay, when you have an interval, is average rate of change. Okay, is an average rate of change. So you know what's your starting value, you know what is the finishing value. So that's a period of time. So it's the average rate of change. You see one point, you see the finishing point, and you compare them. That's the average rate of change. So, well, from in the first 10 seconds is 0 seconds to 10 seconds. So what we will find is V0. That gives you 600. And I can find V10. I'll see the volume at 10 seconds. Minus 1. That's 599. No, wait, 499. So the average rate of change equals to, okay, I use the 10 seconds volume, subtract the beginning volume, divide by the duration, which is 10 seconds. That will give me a minus 10.1. Okay, minus 10.1. What's the unit? What's the unit for this question? Centimeter cube per second. Okay, that's the unit. Centimeter cube per second. This is like V and relate to T. Okay, how V change relate to T. So per second, there's a decrease of volume 10.1 centimeter cube. Okay, if I ask you to answer the question, okay, express it to say what this solution means, you will say there's a decreasing in volume 10 centimeter cube per second. You won't say a minus, okay, you won't say the minus, you say this is a decreasing in volume. You say this is a decreasing in volume of 10.1 centimeter cube per second in the interval of the first 10 seconds. Okay, so that's what you will say. You won't really answer, if you want to express the answer, you won't put the negative in. You won't say there's a change of negative 10.3. You will say there's a decreasing of volume of 10.1 centimeter cube per second. Okay, this negative means a decrease. Okay, for B. B says find the rate of change of volume after 10 seconds. Okay, after 10 seconds. Well, after 10 seconds is like a really, like I can see after that, okay, 10 is my starting value, but I can't see what's my end point. Okay, this is not an interval. It's directly after 10 seconds, what's the rate of change. So this is an instantaneous rate of change. Okay, this is an instantaneous rate of change. It says after 10 seconds, is that moment what's the rate of change. Okay, so what we're trying to find is the V-10. Okay, that's what we're trying to find, is the V-10. So we can find V-T. That gives me minus 10, minus 1 over 50 T. So V-10 is minus 10, minus 10 over 50. That equals to minus 10.2. centimeter cube per second. So at that instant, the volume is decreasing at a rate of 10.2 centimeter cube per second. Okay, at that instant. Okay, for C. How long could the model be valid? Okay, what you're looking for? What? Endpoint? Yes, endpoint. But like when it will be the endpoint? X-intercept? Okay. What equals to 0? There's V and T. y is equivalent to, yeah, y is 0, but in this case we don't have x and y, we have v and t. So v equals to 0, that's right. So it's either say it's the x-intercept, or you can say that's v equals to 0, because x-intercept means like the y value equals to 0, is the volume equals to 0. Okay, so volume equals to 0. You can't have like negative volume, and also like your starting point will be t equals to 0. You can't have negative time as well. You can find the x-intercept on the right hand side of the y-axis, but you can't use the x-intercept on the left hand side, because your time, you have a restriction for time, which needs to be positive, and the volume needs to be positive. So what we'll do is to find the vt equals to 0. Okay, we find vt equals to 0. I can use a calculator to do that. Menu 600 minus 10, or I can use x, 10x minus 1 over 100 times x squared. Make that equals to 0, comma x. Okay, we have two solutions here, but which one we can use? We should use Control Enter to find the approximation value to see what the answer actually is. Well, this is a negative time. Okay, remember your x is the t. Okay, you have a negative time. We don't want the negative time, so we will select the positive time. Okay, this is the positive time. So that's this solution here. 100 root 31 minus 500. So your t needs to belongs to 0 to 100 root 31 minus 500. Inclusive, you can include the volume equals to 0 point. Okay, that's the, okay, we select the positive answer. Okay, we select the positive answer, because negative answer is negative time. We don't want negative time. My time can only start from 0. Any questions for this page? Well, it's basically revision for chapter 9 content. Not much like we need to learn today. If we don't have any questions for this page, can we go to the next page and help me to change this a little bit? Okay, add the endpoint here. A, B, C, let's say that's a point D. And extend this one longer. Well, how long? Depends. Just go above the point A. Okay, just go above the point A. And then at the endpoint there, say that's the endpoint E. Let's say that's endpoint E. Okay, let's talk about the name of all of these points. Okay, let's talk about the name for all of these points. What's point D and E called? Endpoints. Okay, let's write this here. So that's endpoints. What's point A? Yeah, maximum turning point. Good. Okay, what's point B? It's called stationary point of inflection. Well, I'll write the full name. Stationary point of inflection. Okay, what's point C? Minimum turning point. Okay, instead of say that's maximum turning point and minimum turning point, I will add the word local in the front. Local maximum turning point and local minimum turning point. Why I would add the word local is only for this small area, the local area, it is the minimum, it is the maximum. But we look at the big picture for this one. Is that the maximum or the minimum? Is that, well, is A the highest point? No. Which point is the highest point? E. So E got another name. It's called the absolute maximum. Okay, what's the lowest point in this diagram? C. Okay, D is still above that. Okay, C is here. So C is the absolute minimum. Alright, so according to this, let's have a look. Okay, what's another name you can give A, B, and C? What a common name they'll share? Stationary points. Good. That's stationary point. Okay, it's a very beautiful diagram. We have a lot of writing there. Okay, what a common thing that stationary points will share? Derivative equals to 0. Okay, so for stationary point, you have that below. Okay, I'll just write it here. Stationary point f dash x equals to 0. Okay, because for all these stationary points, doesn't matter if it's a local maximum, local minimum, or stationary point of inflection, if you draw the tangent, it will be a horizontal tangent. And it only crosses that local area once. And you have derivative equals to 0. Because the gradient of a horizontal line equals to 0, so the derivative will equals to 0 at those stationary points. And that's the first thing I want to say. And the second thing is, okay, before I said that, why I have an equation, I don't know the diagram, I just know the equation fx, and I derive it, I have f dash x. And I solve it, f dash x equals to 0. I have solved out 3 values, 1, 2, 3. Okay? F dash 1, f dash 2, f dash 3 equals to 0. Do you know immediately that are they maximum, minimum, or stationary point of inflection? No, okay? We don't have that information. Most of you, I think, already learned that in year 11. So when we solve derivative equals to 0, we have a couple of x values. Most of the time will be 2 or even 1. But we don't know the nature. This is called the nature of the stationary points. Well, whether it's a maximum, minimum, or stationary point of inflection. Well, also for the stationary point of inflection, you have decreasing. This is a decreasing stationary point of inflection, or you have an increasing stationary point of inflection. When you solve f dash x equals to 0, you find the solutions. You don't know the nature of those points. Okay, you need a further test to find whether it's maximum or minimum. But that's not. I'm not going to talk about this today. The next thing I'm going to talk about is the absolute maximum and the local maximum minimum thing. Okay, you can think. We only talk about local maximum or minimum. Most of the time we talk about those two things when there's endpoints. Okay, if for example I just give you a polynomial, okay, a cubic. Let's think about the cubic. There's no endpoints, okay, there's no restriction in domain. Are you going to have an absolute maximum? It's just any cubic graph. Are you going to have an absolute maximum? No, it's going to be that, keep going. And you don't have a local minimum either, okay, there's no local, no, absolute maximum or minimum exists on that diagram. Or let's say if I have a quadratic x squared, do you have a local maximum or minimum? Have a think about that. X squared. Hello. Do you have local maximum or minimum? Yeah, true. So even though there's no restriction, I can't find absolute maximum. There's no absolute maximum, x squared, no maximum. But I have a minimum turning point. That will be the local minimum and also the absolute minimum. Okay, the word local is only used for turning point. Okay, only used for turning point. Those ones can't be local maximum minimum. They are only absolute. But like absolute maximum minimum is what's the highest and what's the lowest point of that diagram. So x squared will got a minimum turning point. Okay, like this. You have the minimum turning point, and also it's the lowest, it's the absolute lowest point of that diagram. So you will have absolute minimum for x squared as well. But most of the time when we mention local maximum and minimum thing, we talk about diagrams with two restrictions on both sides, okay, with endpoints on both sides. So absolute. Okay, this is quite important because last year one mock exam really talk about the absolute point, maximum, minimum. If you know this, that question will be very easy to solve. Okay, absolute maximum or minimum only exist among stationary points and endpoints. Among those values, those points, okay? So give you an unfamiliar equation, okay? Give you some unfamiliar equation. You don't know the shape, you don't know anything. Just give you that equation, give you the restriction in domain, like 1 to 5, for example. If ask you what's the absolute maximum for this diagram, or what's the absolute minimum for this diagram, what all you need to do is find all the stationary points, okay? A, B, A, FA, B, FB, C, FC, all the stationary points. You don't need to know the nature. You don't need to know the nature. You don't need to care about that. Just find all the stationary points and find the two endpoints. Okay, left one and right hand side one. So let's say we have 5 points in total now. You compare all the y value. Which y value is the highest one? That's the absolute maximum. And in that 5 points, which y value is the lowest one? That's the absolute minimum. Okay, easy like this. If you don't want any other information, you just want to see what's the absolute max and what's the absolute minimum. What all you need to do is find the two endpoints, find all the stationary points, compare all of these points. You don't need to find the nature of the stationary, but what you need to know is the y value. Okay, 3 stationary points, 2 endpoints. Okay, compare them. Okay, compare them. Which one got the minimum y value? That's the absolute minimum. Which one got the highest y value? That's the absolute maximum. Doesn't matter whether it's local maximum or minimum. If it got the absolute is the highest y value, that's an absolute maximum as well. So same as the C point here. C is a stationary point, local minimum, but it's also an absolute minimum as well. Okay, so among those points, you can definitely find your absolute max and minimum point. So that's one thing you need to know. Because you think maybe it's not that helpful, but for last year there's a mock exam. This is very helpful. Okay, this is very helpful because there's no way you can find the shape of the diagram in exam 1. Okay, in exam 1, you don't know what the graph looks like, but all you need to know is the stationary points and the endpoints. That's easy to find. Therefore, you can find absolute max and minimum. Okay, what all I said here is only find max and absolute minimum. Okay, that's one point. So what I will do next is okay, I'll do example 1. Okay, I don't have enough time to do example 1. I think I might stop here, and then because those two is very important, you might get this in SEC as well. Is using differential calculus knowledge to sketch unfamiliar graph. You might get this as well. You have your calculator, but also you need to know how to do it by hand. Okay, you have your calculator, it's not that hard, but also there may be some leading steps for you to see what you need to do. I'll go through those two questions carefully next lesson. But okay, but like let's just briefly talk about like the slope diagram. Okay, that's a slope diagram. Okay, so according to the gradient on both sides, you can see whether you have local maximum, local minimum, or positive or negative stationary point of inflection. But one thing I really want to emphasize is, let's say we have, just do the easiest one. Let's say we have fx equals to x squared. Okay, easiest one. But so just imagine we don't know what the graph looks like, and I want to sketch it. This is an unfamiliar thing for me. I want to sketch for it. So now I want to find the stationary points, and I want to know the nature of the stationary points. So I will do f dash x. That equals to 2x. And I will solve 2x equals to 0. Give me x equals to 0. That's the stationary points. Okay, that's the stationary points. But suppose we don't know whether it's a maximum or a minimum. So all I need to do is use a slope diagram to test it. Okay, a slope diagram to test it. We need 3 rows. Okay, how many columns we need, it depends on how many stationary points you have. So the first row is x, second row is f dash x value, and the third row is the graph. The first column is always empty because like we need a left-hand side value. And then after that, we write the first smallest stationary point, x value of the stationary points. In this case, we only have 0, so we just have a 0. And we leave another empty column for the right-hand side value. And if you have more, you keep going on the right-hand side. For example, you have 1 as well, so you have a 1 there. Leave another empty, and you have next one, maybe for example, is 2. But we just need 3 columns in this case. Okay, so you know f dash 0 equals to 0, and the diagram is a horizontal diagram, right? That's what we know. Gradient is horizontal. Now what we need to do is select a value on the left hand side of 0 and select value on the right hand side of 0. Okay, what we'll select is easy values. Well, you can select 101, but why do that? Like, it's too hard to do. So we can select just basically 1 and -1 on the left and right to make the calculation easier. Okay, I'm not sure last year whether you have been told this, but according to the teachers who marked the exam, they said you can't only write sign diagram in the second row, you must write values, which means you must solve this into f dash x and find the value. Okay, you know, like all we need to see is whether it's positive or negative. Okay, that's all we want to see and we want to know. It's very easy to, we don't need to calculate. Sometimes, you know, positive add up must be a positive. We don't need to really calculate. Okay, and we can say, a square must be positive. We don't need to calculate. Well, hard to calculate, hard to do the calculation. But VCAT really wants to see the value you substitute. So this is to get marks. Okay, so this row must to put values, not the sign only. Okay, you can't just put positive or negative. All we want to see, yes, is positive or negative, but they want to see values. Because you know why? Sometimes I think students can guess, oh, I'm aiming for a local minimum. This side must be negative, I write the negative. This side must be positive, I write the positive without any thinking or checking. That's, I think they want to minimize. They ask you to sub the top value into the f dash x and really know what you're actually doing there. So we sub -1. Don't sub into the wrong function. I see a lot of students actually sub into the fx and say, oh, I can't get the diagram because you sub into the wrong function. You must sub into the gradient function. I want to see the gradient on the left and on the right. So in this case, I have a -2 here. Okay, make it obvious, we must have values here. And we have 2 on this side. Make sure you sub into the right function, get the right value and right sign. Now what we have is a negative gradient. Well, it doesn't matter how negative is that, you always have a decreasing gradient. And then the other side is positive, so we have an increasing gradient, tangent. So therefore, this point is a local minimum. Okay, this point is a local minimum. That's how we do a sign diagram, and that's the correct way and something you need to be aware of. We need values in the second row. You can't just put plus or minus in those two places. I just know that last year because someone marked the paper and talked about that when we marked the set. They said, some of us say, well, it's silly to just put the values there. You can easily see some positive or negative, but I know they want that actually. Okay, so that's something you need to pay attention and really substitute into the right equation. Don't sub into the fx. Even though you have the right sign, it won't be you won't get the full mark. So make sure you sub into the fx and select the right point. Okay, I'll stop here. Okay, I'll stop here. So you can do the exercise from B and C now. Okay, we complete most of C already. So we're up to C now. So tomorrow we'll talk about D. Okay, we'll talk about D. Any questions? I think you can. That's not like marked wrong. Like it's still a right method. But if you want to use this particular method, you must have the values there. Any other questions?